right, today's topic is about Division 9. Division 9 is about finishes. It's devoted to interior finishes. Today's topic is about ceilings and acoustics. Let's get started with acoustics. Sound is produced when something vibrates. The vibrating body causes the medium water air around it to vibrate. Vibration in air is called traveling longitudinal waves, which we can hear. All right. Sound waves consist of areas of high and low pressure. Sound travels faster through solids and much slower through gas. That's why we can hear somebody really well if we put our ears against something solid. And if we go into the water, we can hear dangling, jiggly elements. But it's much harder to hear when we're in space. Sound travels faster through warm air. There are numbers which we use to calibrate that as well, measure that as well. I'm going to talk in a very simplistic way, so I apologize if it's not as accurate scientifically. So you can go online and get more accurate information, but I'll try to simplify it so we can use it in quick application in architecture. Sound is, as we talked about, is vibration. So we, on a very quick format, we can control the sound by controlling the sound transmission as well as sound absorption. Let's talk about it. So when the sound hits a surface, some of it reflects back, some of it gets observed, some of it transmits through. So when we talk about sound transmission, how much of it transmits through, sound absorption, how much of it is observed. And we look at them together and separately, depending on the type of a project. So when the sound hits the surface, some of it bounces back, some of it goes through, obviously much weaker sound waves, and some of it is actually observed. If we would like it to be observed more, we use fuzzier surface. If we would like to actually have it bounce back, we will have a denser surface. If we would like to combine the two, we will put the fuzzy surface in the front, denser surface in the back. The sound will hit the fuzzy surface, much of it gets observed. Whatever doesn't get observed it hits this area and bounces back again into the fuzzy area and gets observed. Very little of it goes through. So on a little bit more complex, we think about the high sound as it hits the surface versus the low sound as it hits the surface. And if we have a porous surface, that's going to allow that to be observed, or a dense surface, that's going to push it to bounce back. So we're thinking about frequency and sound intensity. Frequency, sound intensity. We're also concerned about background noise. All of these are actually studied separately as well as together. It can get very complex. We try to simplify it for us architects so we can quickly make some sound decisions, good decisions in reference to sound and acoustics. So let's look at a method that architects control the sound, and that's NRC, Noise Reduction Coefficient. It's about sound absorption. It's 0 to 1, and we can actually visually identify what materials are better. The thicker it is, the better it is. So simply size, thickness of the material, the number of pores, number of holes on that surface, irregularity of the pattern on the surface that takes care of different frequency. So when we're looking at acoustic panels that we were looking for to use for the ceiling, the thicker they are, the better they are. The more holes they have, the better it is. And the more irregular pattern they are, the better it is. So don't try to modify it. It's actually this NRC that we're concerned with. Now, sound transmission coefficient. Effectiveness of the sound in terms of blocking, not allowing the sound to transfer through. Effectiveness of the sound barrier. Again, I'm simplifying it so that you can actually understand it and apply it easier. This is a more detailed definition of it. So if you want to stop the sound from passing through, you want that surface, that architectural component to act as a barrier. You're looking for a denser material for higher SDC, and you want multiple layers. If you're looking for noise reduction coefficient, you're looking for something that's fuzzier. It actually allows the sound to get trapped inside of it. STC, sound transmission coefficient, it's measured based on what room you're adjacent. So it has to do with adjacency of rooms. It's an abstract unit of measurement. So we then see these numbers that we get out of time saver standards or some older references that we have that give us specific sound transmission coefficient. Essentially, we get the sound transmission coefficient, STC, for each layer of the building. We add it together and it gives us the total STC. So we get the sound transmission for each layer of the building component, and then we get the total. Granted, it's not uniform because we usually get it over this cross section, whereas we know that the STC over this cross section is substantially different than this cross section. So that's the one we are trying. When we get STC of 40, it's through here and it's not through that zone. So you want to be concerned about that. And then there is a normal versus loud speech and so on that you're looking for STC. And so the higher SDC, the better it is. The higher NRC, the better it is. So the more control you have. So you look at your wall composition in terms of the SDC that you want specific. So this table is out of the graphic standards for architects, and it'll give you the SDC, and it doesn't get that complex in terms of room adjacency. It gives you very basics, but it gives you your basic components and how much SDC you actually can get. The same table actually gives you your fire rating. So you may be interested in a variety of issues in terms of fire rating versus SDC. There is another complex issue, and that's impact insulation class. You're looking at the overall effectiveness of sound and acoustics. And you're actually trying to control the sound so it doesn't go from one zone to another zone. So in that case, you want to look at the source where the sound is being created. So you look at the structure in terms of vibration, and transmission of the vibration. You then look at creation, where it's actually created, and whether you can reduce where the sound is created or you can actually increase it. Sometimes you want to increase it. Most of the times we want to decrease it, control it. Create adding layers to reduce the transfer of the vibration. And remember, sound transfers fastest through solids. So what we like to do is reduce the solids. Remember, sound transfers downward. Heat goes up, sound goes down. And so you want to create these chutes, these drainage channels for the sound to go down without hitting your zone that you're interested, the space that you're interested. Use the NRC, noise reduction coefficient, as well as STC, sound transmission coefficient, effectiveness of a material or a component or a partition as a barrier. So look at all of that as you want to improve the IIC. Now, IIC is very similar to INR. just the reference number, this abstract number and unit of measurement is different, but essentially it's the same. Now watch the comparison. So the INR for basic wood construction, light wood construction, is this. As you go through INR, you recognize that all of the elements that I talked about are far more effective. This is unit 1 of the ceiling.